So good afternoon, everyone. It's nice to be joined by you all today. It's my first time at the Radiance workshop, so I'm a little nervous. Please go easy on me. For those of you that haven't met me yet, my name is Fion, and I am a first-year PhD student studying at University of Toronto. And my supervisor is Alstan, who's sitting at the back. And my research currently focuses on the evaluation of global daylight metrics. And today we will be looking at a comparative analysis of global daylight metrics within the Canadian climate and see how they hold up in the Canadian climate. I'm excited to share my research with you guys, and also excited to hear your thoughts on my research. So this is a quick look at my presentation today. So I'll start by discussing some of the key methods used in daylight assessment with a particular focus on climate-based daylight metrics and the challenges that come with them. And from there, I'll dive into my own research, which is used as a case study in this presentation to explore these issues in greater depth. So before we dive into the details, I want to share why I'm dedicating my PhD to study daylight metrics. Why focus on this, you might ask? Well, accurate daylight metrics are crucial for evaluating how well our spaces harness natural light and identifying areas where we can do better. As we all know, daylight offers multiple benefits, from occupant well-being to reducing energy consumption. But to truly reap these benefits, we need to ensure that our assessments of daylight are precise and meaningful. This means taking a closer look at the existing metrics and performing performance criteria, understanding their strengths and weaknesses, and find ways to improve them. So this is a timeline of daylight assessments. And generally, these methods can be categorized into three main types, and that is static assessment, dynamic assessment, and climate-based metrics. So the daylight factor is a key metric in daylight assessment defined as the ratio of internal to external luminance under a standard CIE overcast sky. That was introduced in 1911 by Trotter, and DF was initially used as legal rights of light, but has since become a standard in evaluating daylight sufficiency. So DF is calculated using the formula DF equals EI over EO, where EI is the indoor illuminance and EO is the outdoor illuminance. Its simplicity has led to the widespread use of this metric in building codes and standards, particularly in the UK and Europe. So typically, a daylight factor of 2% is considered as a threshold by many metrics. And to illustrate why this 2% is considered as a threshold, we can do some simple calculations. So typically, 500 lux on the work plane is often recommended for office work. So let's assume an outside illuminance of around 10,000 lux under an overcast sky. The corresponding daylight factor requirement is simply 500 lux over 10,000 lux, and the daylight factor is 2%. So this aligns with various standards, including the LEED threshold. However, despite the wide use of DF, it has significant limitations. It only considers static conditions under overcast skies and ignores direct sunlight, building orientation, and changing weather conditions. So this lack of context sensitivity can lead to incomplete or misleading daylight assessments. To address the limitations of daylight factor, the daylight coefficient method was introduced in 1983 by Tregenza and Waters. DC allows for more dynamic and accurate daylighting assessments under various conditions. Tregenza initially divided the sky hemisphere into 145 circular patches, and in 2001, Reinhardt further developed this by creating ellipsoid patches that covers the entire hemisphere. So the DC method uses matrix-based operations and finite element methods to calculate internal luminance for multiple points. Let's break down the calculation details and equation for the daylight coefficient method step by step. So first, a sky matrix is created with 145 patches, each contributing to the overall daylight in the interior space, and each sky patch is denoted as A. X represents a point in space. The internal luminance at a point X due to sky patch A is denoted as EAX. This luminance is influenced by the sky patch luminance denoted as LA and its solid angle SA. So the daylight coefficient for point X due to a sky patch A is defined as the equation highlighted on the slide. Here, dCAX represents how much the sky patch contributes to the internal luminance at point X per unit luminance and solid angle. To find the total internal luminance EX at a point X, we sum the contributions from all the sky patches. The equation means that we take the daylight coefficient for each sky patch and multiply it by the luminance and solid angle of that patch, and then sum these values for all the patches. The Monte Carlo statistical sampling techniques such as ray tracing set the foundation for practical computation of DC. Ray tracing significantly reduces the computational load required for annual DC calculations. The DC method can estimate internal luminance and reflect the sunlight for various sky models, taking into account the space geometry, external obstructions, internal surfaces, and glazing properties. One of the main advantages of DC is that it has improved accuracy, at least over climate, when compared to traditional DF method. It also allows for dynamic assessment considering varying sky conditions, latitude, time of the year, hour of the day, and weather conditions. So based on the daylight coefficient method, the notion of climate-based daylight modeling was introduced in 2000. CBDM uses daylight simulation tools to quantify absolute luminance values, considering the variability of sky luminance distributions from representative weather data. So the growth of CBDM has been driven by several factors, and that includes enhanced computing power at affordable prices, widespread proficiency in 3D CAD, and user-friendly interfaces for generating building models and conducting daylight simulations. These advancements together have made it easier to perform daylighting studies. The advantages of CBDM. So CBDM offers several advantages. It enables project development that responds to unique solar and weather conditions of the project site. It considers daily and seasonal variations of daylight, providing a more accurate and comprehensive assessment. It also facilitates the implementation of dynamic daylight apertures, such as automated facade systems or interior shading systems. Additionally, CBDM tools often include advanced visualization capabilities, allowing for effective communication of daylighting strategies through simulations, renderings, and graphical representations. So unlike static daylight factor assessments, which involve single point in time calculations, CBDM requires temporal assessments over specified intervals, such as hourly. This method utilizes the daylight coefficient approach, significantly reducing the simulation time. CBDM considers various factors, as we talked about earlier, includes location, orientation, geometry, material properties, providing a more detailed analysis. So several metrics have been proposed to evaluate performance using the CBDM approach, and these metrics are known as dynamic metrics. Dynamic metrics or climate-based metrics report long-term performance and considers time series of sky luminances. These metrics incorporate temporal and spatial criteria to quantify internal daylight. So let's look at some examples of dynamic metrics. Daylight autonomy, or DA, was introduced in 1989 and later refined by Reinhardt and Wolkenforth in 2001. It is defined as a percentage of occupied times of the year when a minimum work plane illuminance can be maintained by daylight alone. The threshold is commonly set at 500 lux. However, DA has limitations as it does not consider target illuminance below or above the limit. To address the binary threshold approach of DA, Rogers and Goldman proposed continuous daylight autonomy, or CDA, in 2006. CDA assigns partial credit to luminances below the suggested limit, recognizing underlit conditions and providing a more nuanced view of daylight performance. So for example, in the case where 500 lux are required and 400 lux are provided by daylight at a given time step, a partial credit of 0.8 is given for that time step. The result is a softened transition between compliance and non-compliance. maximum daylight autonomy, or DA max, was suggested by Rogers and Goldman in the same year in 2006 to consider overlit conditions. It reports a percentage of annual time steps when luminance levels exceed 10 times the predefined threshold, helping to identify areas with excessive sunlight. Useful daylight luminance, where UDI was developed in 2006. As the name suggests, UDI sets upper and lower thresholds to determine the usefulness of daylight, addressing issues of underlit and overlit spaces. So based on the upper and lower thresholds of 2000 lux and 100 lux, UDI results in 3 metrics. UDI achieved, fell short, or exceeded. The last bin is meant to detect the likely appearance of glare. The threshold was later updated to include 4 bins, and that is UDI, fell short, supplemental, autonomous, and exceeded. Compared to DA and CDA, UDI offers more detailed information on the visual and thermal discomfort, but can be complex due to the multiple thresholds per calculation point. So up until now, the metrics we just talked about only represented temporal occurrences of daylight, where all sensor points can be mapped two-dimensionally. So spatial considerations need to be reported. In 2012, IES LM83 expanded former temporal metrics with spatial considerations, introducing spatial daylight autonomy and annual sunlight exposure. SDA 350% measures the percentage of space receiving 300 lux for 50% of annual occupied hours. It's important to note here that SDA includes dynamic shading in its analysis. And on the other hand, ASE does not account for dynamic shading in its analysis because ASE evaluates the risk of excessive sunlight penetration. ASE at 1,250 hours essentially measures the percentage of space receiving 1,000 lux for 250 hours annually. There are many daylight metrics available, each with different assessment criteria. These requirements can generally be broken down into 3 categories: assessment period, daylight requirements, and the employment of dynamic shades. Daylight metrics typically consider 2 types of assessment periods: daylight hours during the year and occupied times of the year. Daylight hours are directly tied to the building site and remain constant unless the urban environment changes, but they don't account for changing occupancy patterns or building use. On the other hand, using occupied hours reflect the connection between daylight and occupant needs, because daylight needs witnesses to be appreciated. Daylight requirements and metrics are typically defined by 3 criteria: illuminance, time, and spatial thresholds. Illuminance thresholds include target, minimum, and maximum levels. Time thresholds determine percentage of time that space meets these illuminance criteria. Finally, spatial thresholds, like those used in SDA and ASE metrics, assess the percentage of space that meets the illuminance and time criteria. Shading devices, both static and dynamic, are important in daylight analysis. Static devices such as light shelves are often included in assessment without further attention. Dynamic devices like Venetian blinds are handled differently across metrics. Some metrics exclude them, especially for glare assessments, while others include them for realistic depiction of daylight conditions. So now we'll compare 2 internationally recognized daylight metrics, and that is EN 17037 and LM83, in terms of their assessment periods, daylight requirements, and the employment of blinds. These standards have very different approaches to daylight evaluation, which we'll look at in detail. EN 17037 adapts its analysis period to climatic variations by selecting the top 50% or the 4,380 hours with the greatest diffuse horizontal luminance. This ensures that the assessment is suitable for the specific climate of the location. And in contrast, LM83 uses a consistent analysis period of 8 a.m. to 6 p.m. every day of the year. EN 17037 employs a tier recommendation system for interior daylight levels, categorizing spaces into minimum, medium, and high daylighting levels based on the percentage of the area achieving specific luminance thresholds. So for minimum recommendation, at least 50% of the area must achieve a target luminance of 300 lux, with 95% of the area achieving at least 100 lux. For medium recommendation, at least 50% of the area must achieve 500 lux, with 95% of the area achieving at least 300 lux. And lastly, for high recommendations, at least 50% of the area should achieve 750 lux, with 95% of the area achieving no less than 500 lux. On the other hand, LM83 uses metrics like SDA and ASC to evaluate daylight autonomy and potential visual discomfort. As we talked about earlier, SDA 350% evaluates the percentage of space achieving a minimum of 300 lux from daylight for at least 50% of the analysis period. The daylight performance is categorized as preferred if 75% of space meets SDA and nominally acceptable at a 55% threshold. ASC 1250 identifies areas exposed to over 1,000 lux from direct sunlight for more than 250 hours annually. EN 17037 does not factor in the use of shades or blinds in the daylight assessment. In contrast, LM83 incorporates the operation of blinds and shades, adjusting them hourly to manage direct daylight. For SDA calculations, the ASC metric under LM83 does not consider shading devices to assess potential glare. So what is the challenge in applying daylighting standards consistently across one region? The answer is latitudes. The variation in daylight hours across different locations is significantly influenced by latitude, which determines the sunlight duration and elevation throughout the year. As locations move further from the equator, they receive daylight at a more oblique angle and with shorter duration. So let's take 4 Canadian climates, for example, to illustrate this. As Canada spans a wide range of latitudes from 42 degrees to 83 degrees north, it exhibits a significant difference in daylight availability, with northern regions experiencing more pronounced variations. For example, in January, Toronto experiences 9 hours of daylight on average, whereas in Resolute Bay, there is absolutely no daylight. In June, Toronto experiences on average 15 hours of daylight, and in Resolute, the sun is up all day. So such geographic differences in daylight hours introduce some complexities in applying daylighting standards uniformly across one region. So we therefore propose a consideration of latitude when we evaluate the applicability of daylight metrics. So the image on the slide illustrates the research flow where metrics and compliance are generated for 3 office building designs in 4 climates and for 2 types of daylight metrics. The study focuses on the analysis of 2 daylighting metrics, which we talked about. It's EN 17037 and LM83. And 3 designs were selected to cover a wide range of common office building types in Canada, with a particular focus on facade design and its impact on daylighting. Additionally, a light urban context surrounds the office building design, as shown on the slide. The base case model features a fully glazed or curtain wall system, which is a common design in modern office buildings. Despite its popularity, this design is known to present challenges related to daylight, such as potential for glare and excessive closure of operable window shades. Option 1 is designed with daylight optimization in mind. This model incorporates brise-soleil windows to enhance daylight diffusion and reduces glare potential. This approach represents a more careful engagement with daylighting principles in facade design. Option 2 reflects the characteristics of a typical office building from the 1980s. This model has a window-to-wall ratio of approximately 40%. It serves as a benchmark for assessing daylighting strategies in older office buildings that may not have been originally designed with modern daylighting standards. The study assesses daylighting across a spectrum of Canadian climates, specifically in Toronto, Edmonton, Yellowknife, and Resolute. These cities with latitudes of 43.7, 53.5, 62.5, and 43.7 degrees north, respectively, which goes in to illustrate Canada's latitude diversity. Daylighting simulations were performed using Climate Studio. Daylight was simulated using a 6 ambient bounds calculation in a method approximately the Radiance biphase annual calculation with 4,096 primary array samples per sensor. In addition, a Python script was developed to calculate the metrics for this research with the goal of adding additional metrics to automate future analysis. So the evaluation yielded 4 key sets of findings. The first set of findings focuses on the metrics schedule. The 2 tables on the slide compare the average daylight hours available in more extreme climates like Yellowknife and Resolute with the assessment schedules recommended by EN 17037 and LM83. So it's clear from this comparison that EN 17037 offers a more realistic and adaptable schedule, aligning more closely with the actual daylight experience in the climates, whereas LM83 excludes a lot of daylight hours and includes a lot more dark hours in its analysis period. To put this in numbers, EN 17037 accounts for significantly lower dark hours within its daylight schedule. In contrast, LM83's schedule reveals a distinctly higher incidence of dark hours during the analysis. LM83's fixed schedule is less adaptable to extreme northern climates, particularly in cases like Resolute, where over 1,000 hours of darkness are factored into the daylight evaluation. This is a significant misalignment with actual daylight availability in northern climates. When examining the concept of biological night, which spans from 10 p.m. to 7 a.m., we find that EN 17037 standard includes an extensive number of these night hours, particularly in the northern climates. Specifically, the analysis period for EN 17037 encompasses 1,131 night hours in Resolute. This raises questions about its practicality and applicability for occupational activities where adherence to biological rhythm is crucial. The second set of findings focus on the compliance with EN 17037 and LM83 across climates. Only the base case option is shown as a presentation because of its full glazing properties, which amplifies daylighting effects and serve as a more discernible subject for evaluating the data. The results indicate a significant variability in spaces meeting LM83 compliance criteria across different climates. The variability in SDA compliance highlights a noticeable decrease as one moves northward. Similarly, ASC compliance exhibits a decrease in glare issues as one moves north, attributed to the reduced daylight in SDA compliance. In contrast, EN 17037 is more consistent in achieving its minimum, medium, and high daylighting criteria compared to LM83. This uniformity is particularly evident in the medium and high categories, where an identical percentage of the building space fulfills the daylighting criteria across the varied climates. This phenomenon can be attributed to EN 17037's climate responsive scheduling, which enables a more equitable assessment of buildings in diverse climate, and also its rigid spatial unit of compliance, where each room is either fully lit or not. The third set of findings reveal the spatial daylight performance across the 4 steady Canadian climates. The spatial diagrams from LM83 indicate a notable reduction in both sunlight exposure and mean illuminance as one proceeds from Toronto to Resolute. This gradient reveals a consistent decrease in spaces meeting the daylight autonomy criteria towards higher. This latitudinal dependency highlights the potential challenges in LM83's application to geographically diverse conditions, as mentioned earlier. Similarly, EN 17037's assessment across the daylight autonomy reveals levels of 300 lux, 500 lux, and 750 lux demonstrates a similar decline in compliance as latitude increases. All 4 cities exhibit a relatively higher compliance at the 300 lux level, but higher thresholds witness a decline. This suggests 2 possible interpretations. Firstly, the criteria for medium and high recommendations may be excessively stringent for northern climates. And secondly, EN 17037's binary assessment could also be too rigid. The last set of findings compare the building orientation results against LM83 and EN 17037 standards in the 2 extreme climate study, the northernmost and the southernmost locations. So similar to previous findings, the results indicate a notable reduction in compliance levels for both metrics as the location shifts from Toronto to Resolute. For LM83, the north and east orientations demonstrate the highest compliance levels, whereas for EN 17037, the north and south orientations exhibit the highest compliance levels. So this disparity highlights key differences in how these 2 metrics assess daylight performance. LM83 includes blind in its analysis, reducing compliance on the southern facade to mitigate excessive daylight. Unlike EN 17037, for instance, in Resolute, 0% SDA corresponds to over 20% in ASC due to direct daylight exposure without accounting for blinds. This difference shows the impact of blinds on daylight quality assessment, revealing a limitation in Almedy-3's approach where the use of blinds can prevent significant portions of spaces from meeting the criteria. So to sum up, the study found that EN 17037 schedule aligns closely with actual daylight hours, reducing dark hours and making it more adaptable in northern climates. However, it also includes hours during the biological night, which questions its practicality for occupational activities. On the other hand, Almedy-3 aligns better with typical occupant hours and includes strict shading requirements, enhancing visual comfort. Both EN 17037 and Almedy-3 have stringent higher daylight recommendations. EN 17037's room-based compliance approach contrasts with Almedy-3's sensor-based evaluation, which might better capture the nuanced daylighting needs of diverse spaces. The findings also highlight the need to develop an improved daylighting metric that harmonizes daylight availability with actual occupancy. This new metric should also consider both daylight hours and occupancy periods, combining the adaptability of EN 17037 with the practical user schedule of Almedy-3. An adaptive schedule could flexibly adjust to both seasonal daylight variations and typical occupancy patterns, ensuring assessments are relevant when spaces are in use. The schedule shown in pink here on the slide responds to both Almedy-3's typical office hours and also EN 17037's daylight hours. When using this new combined schedule, we find that it eliminates dark hours from occupancy periods, resulting in more consistent DA300 results across Toronto, Edmonton, Yellowknife, and Resolute. This approach demonstrates the potential for fair and effective daylighting across various climates. So what is next for my research? There are numerous global daylight metrics available, each offering a different approach to evaluating daylight quality. We've only touched upon two in our presentation today, and my research aims to systematically compare and analyze various global daylight metrics to gain a deeper understanding of how daylight is assessed across different contexts. In our next research, we will be comparing 35 daylight metrics in 30 climates and further developing our Python script to automate the assessment process. I hope my research can not only evaluate the effectiveness of existing metrics, but also provide guidance for the future design of daylight metrics and assessments. Thank you very much. If you have any questions, I'm happy to answer them. Yes, but not for now. So for now, I think we're going to analyze more daylight metrics. We're going to look at all of these metrics on the slide, but I think maybe in, I don't know, maybe like later on we can look at that as well.